Okay, so my screen is visible, right? My screen is visible?
Yes, ma'am.
Okay. Today we'll be continuing our discussion on how to do state space modeling of a system. So we saw that in our previous classes, we saw that in case of a state space representation, what we need to do is that first of all, we need to write the differential equation model or the differential equations which are governing the dynamics of the system, like the input-output relationship in form of a differential equation. We have to write that one down. So depending on the type of the system or the order of the system, you will have either a first order equation, second order equation, or maybe an nth order equation. So the main task while making or while designing or developing this state space model is that if you have an nth order differential equation, what we need to do there is that we have to break down that nth order differential equation into n number of first order differential equations. Okay, and those differential equations will be in terms of certain variables which are known as state variables. Okay. So if you see the general formula of the state equation, so we have x dot equals to ax plus bu. So x dot, so x is basically the state variable, or you can say that x is the state vector, because here since we are considering there are multiple states, many number of state variables in a system. So x here will be a state vector. So then the first order derivative of each state vector will be reflected on the left hand side of the equation, which is given by x dot. Okay, so now let's do one more example, then things probably would be much more clear. So let's say that if you have been given with a transfer or with a block diagram which looks something like this. Okay, so if you remember that we have already told that if depending on the number of integrators that are present in any circuit or in a system, so that will basically govern the number of state variables present in your system. So we know that the output of integrators, they basically represent a state variable. So if you have like n number of integrators in your system, then the output of each integrator block will be considered as one state variable. Okay, so if you observe this block diagram, you see that we have three integrators. So this is 1 by s, this is a perfect integrator, and these two blocks, this 1 by LAS plus RA and similarly 1 by KT by JS plus F, these two are also integrators, but not like simple integrators. Okay, so we can say here that since we have three integrators in this system, so we have three integrators. That means we can write that we have three state variables. Okay, so now let's denote those state variables as x1, x2 and x3. Output of this integrator is denoted by x1, this is x2 and this is x3. So then what we would, in order to find out the state space model of this system, so what we would need to do is that we have to write the equations corresponding to these from this block diagram with these as with the state variables as our variables. Okay, so let's start from this one. So first of all, you see from the right hand side if you start. So before starting, so we have the input. So input here is VA of S is basically your input. So let's write it as US, and the output of your system is X3. Okay, so we can write that YS is equals to X3 of S. Okay, so just remember one thing is that whenever we are writing it in short, like x1, x2 and x3, if we are writing it in small letter form, then we are representing the state variables in the time domain, that is they are functions of time. But here, since in this block diagram all the blocks they are in the frequency domain, so you should not get confused that this is like just simply multiplying x1 with this one by LAS plus RA. This is not going to help. You have to remember that this small x1, small x2, small x3, these are variables in the time domain. However, these blocks, they are in the frequency domain. So corresponding to this x1, so in the time in the frequency domain it would be x, capital X1 x, corresponding to x2 it will be x2 of s, and corresponding to x3 you will have x3 of s. Okay, so when you write the equations from the block diagram, you have to use this frequency domain or the Laplace transform variables of this x1, x2 and x3, and then finally you can do an inverse Laplace and then find out what will be the differential equation. Okay, so now let's try writing these equations. So first of all, you can see that if you see from the right, so you can say that x3 will be equals to x2 into 1 by s. Okay, and if you take the Laplace inverse of this one, so in time domain you can write that x3 is basically equal to, or you can write s into x3 is equals to x2. So you can write that x3, so this is nothing but x dot, x3 dot, so x3 dot will be equals to x2. So this is one equation that you have. Similarly, you write the equation for this one. So you for this one you have kt by js plus f is multiplied by x1 is equals to x2, right? So from here you can write kt into x1 equals to js x2 plus f into x2, right? And s into x2 is nothing but x2 dot. So in the time domain you will have kt into small x1 equals to j into x2 dot plus f into small x2. You can rearrange this equation and you can write that x2, or you can write j x2 dot is equals to kt into x1 minus f into x2. So this is your equation number 1. You can say this is equation number 2. Okay. Similarly, for this one you will have x1. So 1 by LAS plus RA multiplied by VA minus x2 into KB will be equals to x1, right? So we'll write the equations again. So x1 is basically equals to 1 by LAS plus RA multiplied by VA minus KB into x2. Okay, so from here again you can just simplify and you can write that. So LA into S x1 plus RA into x1 is equals to VA minus KB into x2, right? And then if you take the Laplace inverse, so this x into S into x1, if you do the inverse Laplace, so this is nothing but x1 dot, right? So you can write in time domain, so LA multiplied by x1 dot is equals to minus RA into x1 minus KB into x2 plus VA, and VA is equal. So this is your equation number 3. So these are the 3 equations which will be governing, which you can find from the transfer function, from the block diagram that is given. Okay. So now what we can do is that we have to write them in the vector form. So you will write x1, x2 dot, x3 dot, and you will form the matrix. So corresponding to this one, so you have x1, x2, x3 over here. Then you will have something multiplied by u. Okay. So for x1 you can see that for x1 dot, so it will be minus RA by LA multiplied by x1. Similarly, this one will be minus KB by LA, and there is no term corresponding to x3, so this will be 0. Then for x2 dot, so for x2 dot we had seen that x2 dot is equals to kt by j into x1 minus f by j into x2. So we'll write kt by j will be here minus f by j over here, 0 over here. And x3 dot, so x3 dot is equal to x2. Okay, so that means there will be 0, 1, 0. And for in case of x1 dot also we have something corresponding to the input. So VA is equals to u. So here, so that will be 1 by This term is 1 by LA and the other 2 will be 0. So you can express the three first order differential equations in a matrix form, and this is the generalized form. You can write that in general form. So x dot is the vector. This is equals to A into x plus B into U, where A is this matrix and B is this matrix. Similarly, if you write the output equation, so the output basically we have said that the output is equals to x3. So you can write, if you write y is your output, then your output is equals to x3. So that means 0, 0, 1, and here you will have x1, x2, x3. Okay, so this is basically these two equations. So this is the state equation and this is the output equation. So if you have been given with a block diagram representation of a system, from that block diagram also you can find out the corresponding differential equations, and from that you can write what will be the state space representation of the whole system. Okay, so depending on the type of system or the representation of the system which is given, you can go back and forth. You can, from the state space also, you can go to the transfer function. From the transfer function, you can find that state space. Those things will come later on. Okay, so these are a few examples where, so these two electrical circuits are given. So what you have to do from here is that you have to write the differential equations corresponding to these circuits, and from the differential equations you have to figure out that which variables will be your corresponding state variables, and you have to express the differential equations in terms of first order differential equations, such that your main aim is that you should have an equation which looks like in this form: y equals to cx plus du. So this is the general form. So in this form, so you have to select the values of x accordingly, and depending on what will be the value of C, L and R, that will govern what will be the matrix A, B, C and D. All this matrix will come from the differential equations that you write from the circuits. Okay. So next, so in general, you can say that in general, this is the form of representation of a state variable or a state space representation of any system. Okay, so now depending on the form or the representation of this matrix A, so that matrix A, B, C and D, all these matrix, they can be expressed in different forms. Okay, so there are so you can say that the state space representation, so there are three, we can express them in three different kinds of forms. So one is known as the phase variable or controllable canonical form. Okay, so what are phase variables? Basically, phase variables, they are defined as those state variables which are generally obtained from one of the system variables and its derivatives. So usually what we do is that usually in general practice, so the state variable, the system variable that we take is the output, and all the other states, they are expressed as the derivatives of the output. Okay, so let's say that you have been given, so that you have a system and the differential equation which is governing the system is given by this. So you have y, nth order derivative of y plus a1 into n minus 1th order derivative of y till this a n into y, and on the right hand side you have b0 multiplied by u, where u is the input. So you have nth order derivative of u plus b1 into n minus 1th order derivative of u, and so on and so forth. So if you simply take the Laplace transform of this differential equation, you will end up with a transfer function which looks something like this. So in the numerator, you have b0 is to the power n plus b1 is to the power n minus 1 till bn, and in the denominator you have s to the power n plus a1 is to the power n minus 1 till an. Okay, so now if you want to express, so now you already have this differential equation. So from here you can express, you can sort of simplify this differential equation, or you can split this nth order differential equation into n first order differential equations. So once you do that, then if you write the then this, if the expression, if you write the state equation for this corresponding, for this specific equation, so in general if you express it in this term, so this is your the vector, that is x1 dot x2 dot till xn dot, and then these are your state vectors. So that is x1, x2, x3. These are your state variables. U is the input to your system. Y is the output. Okay, and if your the coefficients were like the coefficients for corresponding to these were given by a0 from a1 till an and b0 till bn. So if you can express the matrix A in this form, where you see that only the bottom or only the last row, basically that has all the negative, all the coefficients with a negative sign. And if you observe that for this part, so corresponding to this part, basically this is nothing but a diagonal matrix. Only the diagonal elements are present, all the other elements are 0. So in this form of representation, this is known as phase variable or controllable canonical form of representation of the state space model. Okay, and in this case, the value of y will be given by the matrix C will be given by the first term will be bn minus an minus b0. So we'll actually not go into the proof for how we can come and derive the or how from the given differential equation we can find this form. We'll not go into the derivative. It's just for your information that this is this type of an expression. This is known as the representation in state variable or controllable canonical form. So here you see that the matrix A, it has all ones in the upper of diagonal. So this diagonal elements are all 1, and the last row comprises of the negative of the coefficients of the original differential equation. So the original differential equation has these terms. So these will be in the last row. So this type and all the other elements are equals to 0. Okay. So this is the expression for, or this is the representation in phase variable form or controllable canonical form. Similarly, there is another type of representation of the state space. So this is known as diagonal canonical form. So this is very important because that mostly if you can express the matrix A in form of a diagonal canonical form, that it becomes the corresponding analysis becomes much more easier. Okay, so for that what you need to do is that, so if we are dealing with the same function which we had seen earlier. So the transfer function is given by this. So here what we need to do is that you have to express this transfer function in this kind of a form. So b0 plus summation of this Ci by S minus lambda I. Okay, so this lambda I, basically they are the poles of this transfer function, and Ci is the residue of the poles at each pole position at lambda I. Okay, so if you can express this term in this transfer function in a form like this, so you have, so this is basically b0 plus you can say that C1 by S minus lambda 1 plus C2 by S minus lambda 2 plus till you get Cn S minus lambda n. Okay, so if you can express it in this form, then you can write that the state equation can be written like x1 dot will be equals to lambda I into xi plus u, and the output y will be equals to c1 x1 plus c2 x2 till cn xn plus b0 into u. And if you simply write these two equations in form of that matrix, so you will see that this A matrix here is a diagonal matrix, and all the diagonal elements, this lambda 1, lambda 2, all the diagonal elements of this matrix are basically nothing but the poles of that corresponding system. Okay, so this is another form of representation for this state space model. So here this is important because if you can express it in diagonal canonical form, then since all the other terms are 0, you are left with only the diagonal terms, then the subsequent analysis of the system that becomes easier. Okay, and the output equation will be given by, so the matrix C will have all the residues at the corresponding values of the poles. So C1, C2 till Cn, and then you have B0 plus U. Okay, so this is the diagonal canonical state form, where the system matrix A is basically a diagonal matrix with the poles of the transfer function as the diagonal elements. Okay, And if you observe the matrix B, so all the elements of this matrix B, they are 1. And similarly, for this row vector C, that has the elements of this row vector C are the residues of the system poles. Okay, so this is the diagonal canonical form representation of the state space model. Okay, similarly, there is one more type of model which is known as Jordan canonical form. So Jordan canonical form is basically, you can say that it's a modification or it's an extension of the diagonal canonical form. So in case that if your system has multiple repeated roots, so in the previous case we had seen that, in this case we had seen that the roots of this transfer function or the poles of this transfer function were distinct. So distinct means all the poles have different value. So there are no repeated or multiple poles at a certain position. Okay, but in case if you have a system where you have repeated roots or repeated poles, so let us say that at s equals to lambda 1, you have 3 poles. So lambda 1 is equals to lambda 2 is equals to lambda 3. So in that case, you can express this transfer function in a form which looks something like this. So you will have C1 by s minus lambda 1 whole cube plus C2 by s minus lambda 1 whole square, and so on and so forth. Similarly, you can write the output equation in this form. And once you have written the output equation as well as the state equation in this form. So from here, what you can do is that you can simply write in the vector form. So vector form will look something like this. Okay, so in this form you see that for the first 3 terms, so this is basically, so this part will comprise of the because of the repeated roots, and rest of the matrix will remain same. The form of the rest of the matrix will remain same as the diagonal canonical form. So here also you see that all the other elements are 0 except the diagonal one. But in case for the first 3 cross 3 elements, you see that since there are these are basically the repeated poles or repeated roots of your system. So that's why this type of the first 3 cross 3 elements, they will be represented in this form. So this will not be a proper diagonal matrix, you can say. So this type of an expression is known as the Jordan canonical form. Okay, so this is valid only if your system has multiple roots or if your system has multiple poles at a particular position. In that case, you can no longer represent your system in simple diagonal canonical form. You have to go for a Jordan canonical form. Okay, so these basically you just have to remember like how the expression looks like. But the most important one is the diagonal canonical form. Okay. So this is just another example. So you have been given with a transfer function, and you have to write the representation in the controllable canonical form as well as the diagonal canonical form. So from here, what you can do is that you can find out what will be the values of the coefficients. So that means A1, A2, then B0, B1, so on and so forth. You can find out all these coefficients, and from the coefficients you can use the general form of expression for the representations, and just by substituting these values you can find what will be the corresponding representation, controllable canonical form representation as well as the diagonal canonical form representation. So now we'll see that, okay, fine, so now till now we have seen that how to write a state equation given that if you have a proper physical system. So from a physical system you write the differential equations, and from the differential equations you write the state equations. Okay, similarly if you have been given with a block diagram, so from the block diagram you can find out what will be the corresponding state space model of the system. Okay, so now we'll talk about how to find out or how to derive a transfer function of a system given the state equations. Okay, so now let's say that you have been given with a system whose state space representation is something like this. So you have x dot equals to ax plus bu and y equals to cx plus du. Okay, so what you need to find out is that you have to find out what will be the transfer function of this system. So the transfer function will be given by gs equals to ys by us, because ys is your output and us is your input. Okay. So for that, what we'll do is that we'll simply take the Laplace transform of these two equations. So from the first equation, you can see that the Laplace transform will be s into xs minus the initial condition x0 equals to a into xs plus b into us. And from the second equation, you will get y of s equals to c of c multiplied by x of s plus d multiplied by u of s. Now, if you remember the definition of a transfer function, so the definition of transfer function was that it is the Laplace transform of the output to the input, given that the initial conditions are all 0. Okay, so if we have to find out the transfer function using this Laplace transforms, then we have to assume that the initial conditions are 0. So that means the value of x0 is equals to 0. Okay, so you just simply make this x0 is equals to 0. Okay, so if you make this x0 equals to 0, so you can write this equation as s into xs minus a into xs equals to b us. And this can be, if you take this xs out common, so you will end up with s into I minus a, where I is basically an identity matrix. So here, since we are dealing with matrix algebra, so that means we cannot simply just, in case of a scalar, when we were dealing with scalar things, so scalar quantities, so we could have just written x into xs minus, let's say, a into xs, if will be equals to s minus a into xs. This would have been valid if this were a scalar quantities. Okay, but now since we are dealing with vectors, so here this value of x, a, these were all scalar values. Okay, so but now in case of a state space representation, this value, this xs, a, b, these are all vectors, right? So that means we cannot simply write s minus a, so we have to multiply it with an identity matrix. So it will be s into I minus a into xs will be equals to p into us. Right, so from here you can write that the value of xs will be equals to s minus ia, this matrix, the inverse of this matrix multiplied by b into us, correct? And from the second equation, so for ys you can just simply substitute the value of xs that you have got. So xs was something like this, so c multiplied by si minus a inverse multiplied by b, that is into us, so you can take us common, so then plus d is equals to us, right? So from this expression you can see, so this is ys, so from here you can write that ys by us will be equals to gs. Okay, so if you compare these two equations, you can see that the value of gs, that is the transfer function of the system, is given by c multiplied by si minus a inverse multiplied by b plus d. Okay, so that means that if you know the state space representation of a system, so you know the state space representation means the value of a, b, c and d, all these vectors are known to you. So simply from the state equations you can directly find out what will be the transfer function of the corresponding system just by using this equation, that is gs will be equals to c si minus a inverse into b plus d. Okay, so this is the expression, this is the expression for transfer function, deriving a transfer function from the state equations. Okay, so now if you see that if there is no direct coupling between the input and the output, in general whenever we are dealing with any kind of a control system, in most of the cases there is no direct coupling between the input and the output. Okay, so that means this quantity d is equals to 0. Okay, so that means you can, in those kind of cases you can write that the transfer function will be simply equals to si minus a inverse multiplied by b. Okay, so in that case you can simply write it like this, and this inverse is the inverse of this matrix si minus a, that is nothing but adjoint of this matrix divided by the determinant of this matrix. So this is the expression for matrix inverse. So, and from this equation you can write that this si minus a inverse, this term is basically known as, you can represent it in terms of phi s, and this is known as the resolvent matrix. Okay, so one thing that you have to study over here is that since in this case for state space modeling or state space representations or state space analysis of a system, so it is very important that you know how to do this matrix algebra. Okay, so you have to you might have already obviously you already know, but just if you have forgotten, then I would suggest that you go and better revise like this basic matrix algebra, like how to find out the determinant, how to find out the inverse of a matrix multiplication, then how to find out the rank of a matrix. So all these simple matrix algebra or this matrix calculations, these you should be able to do, because otherwise without that you won't be able to solve this state space equations. Okay, so that is one thing that you need to revisit in case you have forgotten. Okay, so now let's take an example. So let's say that you have been given with a system. So the state equations of a system is given. Okay, so that means this value of a, b. So the state equation given is x dot is equals to ax plus bu and y is equals to cx plus du. And the values of a, b, c and d are given. Okay, what you need to do is that you have to find out the transfer function of the corresponding system. So if you simply use the equation that we have found, so the equation was that the transfer function gs was equals to c into si minus a inverse into b plus d, right? And in this case d, the value of d is equals to 0, so you can simply ignore this. So this is equals to 0. Okay, so now what you will do is that you will substitute all the matrices. So A, C matrix 1, 0, then Si minus A inverse. So you have to find out that. So Si is nothing but this S0, 0, S. B, A is already given. So you write A over here. Then you have to take an inverse and then you have B. So B is 0 and 1 by M. So from here you just take this subtraction and then so you will end up with something like this. So you have, this is your C, this is your Si minus A inverse and multiplied by B. So if you find the value of this Si minus A, this matrix, so this one will be given by, if you just solve for, so this A, if you have to find out the inverse of a matrix A, that is given by adjoint of that matrix A divided by the determinant of the matrix. So using this equation, you can find out what will be the value of this inverse matrix. Okay, so this is the inverse of this matrix. So what you will, in the next step, so you will write, so 1, 0, then you will substitute this in the middle and then you have 0 and 1 by M. So next what you have to do is that you have to do the matrix multiplication of these two matrices. Okay, and since this is basically, this term is basically a scalar term, this doesn't have any matrix involved in it, so we can just simply take it to the front, and then once you have multiplied these two matrices, then the resultant of these matrix you have to multiply with this matrix and finally you will end up with this equation. Okay, so and this is the form, or this is the transfer function of the system whose state equations is given by this. Okay, so if you are given with the state equations, using the formula that we have just derived, we can find out what will be the corresponding transfer function for the system. Okay, so then I have given you similar some examples, so for you to solve and to practice and see like what will be the transfer functions corresponding to the systems whose state equations are, or the state models are given by this. Okay, so we saw that how to find out the transfer function given the state equations. So now can we do the reverse? So can we find out the state equations if the transfer function of the system is given? Okay, so for that what we need to do is that, let's say that you have been given with the transfer function which is gs. So gs is equals to nothing but ns by ds. So n is the numerator, d and ds is the denominator polynomial. So we'll say that the value of gs is strictly rational if the degree of the numerator is less than the degree of the denominator. If this condition is satisfied, then the transfer function is given as gs is equals to c si minus a inverse into b. But in case this condition is not satisfied, if ns is great, if the numerator polynomial, the order of the numerator or the degree of the numerator polynomial is greater than that of the denominator, then gs is not strictly rational. Then what we have to do is that we have to express this the given transfer function in a form like this. So you will have to express it in terms of d plus g into s, where gs is basically a strictly rational transfer function or strictly rational fraction, you can say. Okay, so in that case, the transfer function will be given by C Si minus A inverse multiplied by B plus D. Okay, so let's just see an example. So let's say that you have been given with GS is equals to this. So in this case, the denominator polynomial degree is greater than that of the numerator. So that means GS is a strictly rational transfer function. So here what we'll do is that, so GS is equals to nothing but y by u. Now what we'll do is that we'll introduce another, so we'll write this in this form. So y by x1 multiplied by x1 by u. Okay, and we will write this in such a form that y by, so x1 by u is equals to k by this form and y by x1 is equals to 1. Right. So if we multiply these two, you will end up with the equation that is already given. Right. So from this equation, you can write that k into us will be equals to this polynomial multiplied by x1, and similarly for this one you will get ys is equals to x1s, right? And if you remember that the transfer function means that it assumes zero initial condition. So that means that the above this this equation is the transfer function. Since we have derived these equations from the transfer function itself, so we can write that, we can say that this is the transfer function of basically a third order differential equation with zero initial condition. You see that the highest power of s is 3, so that means this will be a third order differential equations. And since we are talking about transfer function, so that means the initial conditions will be equals to 0. Okay, so from this equation, what we can do is that we can write we can take the Laplace inverse and we can write the corresponding differential equations, right? So the differential equations will be equals to, so we have here s cube plus a2s square. So we had s cube plus a2s square plus a1s plus a0 multiplied by x1 is equals to k into u. Right, so if we take the Laplace inverse, so you will get x1, so third order derivative of x1, so x1 third order derivative of x1 t, then a2 multiplied by second derivative of x1 plus a1 multiplied by first derivative of x1 plus a0 into x1 will be equals to k into ut. Right, so now you have a third order differential equation. What you need to do is that you have to express the third order differential equation in form of 3 first order differential equations. Okay, so for that what we'll do is that, so we'll take x1 dot and we'll take two other variables. So let us assume that x2 is equals to x1 dot and x3 is equals to x2 dot, and using these two forms we will express this equation. Okay, so from this equation you can write, so x2 is equals to x1 dot and x3 is equals to x2 dot, means you can write this is equals to x1 double dot of t, and x3 dot is equals to x1 triple dot, right? So you can express this as x3 dot, so x3 dot will be equals to minus a2 into x1 double dot. X1 double dot is nothing but x3. Then you have minus a1 into x1 dot. X1 dot is nothing but x2. So you write x2 over here. Then you have minus a0 into x1 plus k into u. Remember that on the right hand side of the state equation, we do not have any derivatives, right? We have only a first order derivative on the left hand side of the equation. Okay, so you have to substitute the variables in such a way that on the right hand side you only have the state variables, and on the left hand side you have the derivative of a state variable. Okay, so this is one differential equation. The other two you can write that x1 dot is equals to x2, x2 dot is equals to x3, and y is equals to x1. So now you have three differential equations, and this is your state, and this is the output equation. So you can simply rearrange, or simply from these three first order differential equations, you can write them in the vector matrix form, and it will be given by this, right? So this is your output equation. Okay, and this is your input, or this is your state equation. So if you have, so by in this process, so depending on the transfer function which is given, whether your transfer function is strictly rational or not. If your transfer function is not strictly rational, in that case you have to just divide it And so that you get a term D plus GS, you have to express the transfer function in this form, and then from there you can write the expression like this. Okay, so in that way you can find out what will be the state equations if the transfer function of the system is provided to you. Okay, so similarly in this case you see that these are the examples that you have to solve at home. So this is a equation where this is strictly rational. So you can just simply use the previous method and find what will be the state equations. Similarly, this is also strictly rational. But in this case, you see that this is not a strictly rational function, because both the powers, the degree of both the polynomials, they are same. So that means what you need to do is that you have to write it in this form, right? So D, so you have to express it in form of D, where D is a scalar quantity plus G into S. Okay, and similarly, if you write GS in form of this, so your output will similarly become ys will be equals to y1s plus d into us. Okay, because your input, basically your gs is nothing but ys by us. Okay, now if you express this as s, so that means you can write ys will be equals to d into us plus gs into us, and gs into us you can just write this is us, that is sum y1 into s. So you find out this y1 into s from this equation and then simply add this d into us, and you will end up with the final output equation. Okay, so these are some problems for you to practice at home. Okay, so next we'll talk about something which is known as a transfer matrix. Okay, so what is a transfer matrix? So in case if you have a multiple input, multiple output system, so let's say you have like R number of inputs to your system. Okay, so those R number of inputs are U1 till UR. Okay, and the outputs are, let us say that you have M number of outputs. Okay, if you write the output and the input of input vectors, so y will be equals to this vector where y1 y2 till ym, and the u input vector will be equals to u1 u2 till ur. Okay, so if your output and input, they are related by this equation or this form, that ys is equals to gs into us, in that case GS is known as the transfer matrix. Okay, so GS transfer matrix that relates the output YS to the input, and generally this so in case if you have an M number of outputs and R number of inputs, then the transfer matrix it is an M cross R matrix. Okay, so then we'll see that how to derive the state equations. So we have seen how to derive state equations from transfer function, or how to write how to find the transfer function from the state equation. Now we'll see how to relate the state equations with the signal flow graphs. Okay, so this is a common by this time you should remember this by heart, that is the output of integrators, they serve as the state variables. Okay, so if you have been given with a signal flow graph which looks like this, so what you need to do is that you have to write the from this signal flow graph you have to write the first order differential equations, and from the first order differential equations you can write the state space representation or the state equations, right? So here you see that you have 1, 2, 3 integrators are present in this signal flow graph. So the output of each integrator will assign that the output of this integrator, this is x1, this is a state variable x1, this is another state variable x2, and this is another state variable x3. Okay, so the moment you have x1, x2 and x3, so that means you can write that the node which is previous to that, so this one will be nothing but x1 dot, because x1 dot multiplied by an integrator will give you x1. Similarly, the node before this one will be x2 dot, and this node will be x3 dot. Okay, so now what we'll do is that so the state variables are x1, x2, x3. These are the state variables of my system. Okay, so now what we'll do is that we'll simply write the equations from this from this signal flow graph. So let's start writing with this equation x3 dot. Okay, so this is x3 dot. So x3 dot will be equals to, so you have b3 multiplied by, so this is nothing but u, because u is getting multiplied by 1, and so this is 1, this is us is getting multiplied, so you have b3 into u. So now remember that since I'm writing it in form of differential equation, I will no longer have the s term. I will express these in terms of in the time domain. So I have b3 into u plus I will have minus a3 multiplied by this this vector. So this is, let's say, y dash if I write. So y dash minus, no minus, I have only this one, and y dash is nothing but, so you have this x1 plus this one b0 into u. Right, so you can simply write that x3 dot will be equals to b3u minus a3 x1 minus b0, or you can write a3 x1 minus b0 into u, sorry, b0 plus u. Okay, similarly you can write the equations for x2 dot and x1 dot. So x2 dot will be equals to x3 plus, so x2 dot is equals to x3 plus b2 multiplied by u minus this one minus a2 multiplied by y dash. So y dash is equals to x1 plus b0 u. Similarly, x1 dot will be given by x2 plus b1 into u minus a1 x1 plus b0 u. And the final output equation was y is equals to y dashed. So this is equals to x1 plus b0 into u. Okay, so now you have three. So this is first, this is second, this is third. So you have three equations. So you can simply write the from these three equations, you can simply write the state space or in the state form you can write. So on the left hand side, you will have x1 dot, x2 dot, x3 dot will be equal to so for x1 you have, this is minus a1, this is minus a2, you have minus a3. So you have minus a1, 1, 0, minus a2, 0, 1, minus a3, 0, 0. And here for the y you have b1 minus a1 b0, b2 minus a2 b0, b3 minus a3 b0 multiplied by u, and the output equation y is equals to 1, 0, 0, x1, x2, x3. Right? So that means from the state, so these equations you will be able to find out the state equations you can write simply from the first order differential equations that you have found out. So you just separate out and you write these in form of a vector matrix where on the right hand side you have the variables, the state variables as well as the input. On the left hand side you have the first order derivative of the state variables, and in case of the output equation on the right hand side you will have both the state variables. You might have the input, you might not have the input depending on how your system is connected. Okay, so similarly if you have so this was like from the state space equation to the from the state space equation, or rather state equations from the signal flow graph. In a similar way, if you go back, if you want to do the reverse way, that is if you have the state equations, if you want to find what will be the signal flow graph. So first what you will do is that you will write the first order differential equations corresponding to these state equations. So for this system, so your x1 dot will be equals to x2 then x2 dot will be equals to minus 3x2 plus x3 plus u, and x3 dot is equals to minus 3x1 minus 4x2 minus 5x3 plus u, and your output equation is x1 plus 2x2 2x2. Okay. So now if you want to draw the signal flow graph, so you have like 3 state variables, so x1, x2 and x3. So first what we'll do is that we will you will identify the state variables, you will draw the path. So let us take that. Okay, so let me take that this is my x1. If you connect this, so that means this will be an integrator, so this will be x1 dot. Similarly, if this is x2, so the node before that would be x2 dot, and this will be an integrator. If this is x3, then the node previous to that will be equals to x3 dot, and this will be an integrator 1 by s, right? And then you will have an output y somewhere over here and an input which is equals to u somewhere over here. And then what you will do is that simply from these equations, you will draw the signal flow graph. So that means from the first equation, you see that x1 dot is equals to x2. So you will connect these two nodes and the gain will be equals to 1. For x2 dot, what you have is that minus 3 into x2. So that means there will be something like this, minus 3. Then you have plus x3, so that means you connect these two, this will be 1, and you have another input for u. Okay, so u will come directly over here with a gain of 1. Okay, similarly if you see the third one, so in the third equation you have minus 3 into x1, so x1 is here, so you will have minus 3 over here, then minus 4 into x2, so you will have one more from x2 with a gain of minus 4, minus 5 into x3, so from x3 you have minus 5 over here, and u is directly coming over here as 1, right? And in the output, so output is basically x1, so you have to connect these two with a gain of 1 and 2 of x2. So x2 is over here, so x2 will, you will join here and it will be equals to 2, right? So this will be the overall signal flow graph from the state equations. So from this way, so the basic thing remains the same, that is you have to find out n number of first order differential equations. So if you can find out n number of first order differential equations, then you can express those differential equations and provided that those n number of differential equations, they are in terms of the state variables as well as the input variable. If you express the differential equations in that form, so from there you can find out what will be the state equation and the corresponding output equations. Okay, so is the concept of how to write the state equations and these things are clear to you, or do you have any doubts? Any doubts till now? Okay, so I'm guessing since no one is responding, so I'm guessing that you have understood everything. So that's all. Let's wrap up today's class. We'll again have our class tomorrow, where we'll continue discussing on the state variable or state space analysis for different other kinds of systems. We'll talk about some discrete time. So instead of continuous time systems, we'll talk about discrete time systems as well. So that's all from my side today. Thank you, everyone.